All right. Yes. Thanks, Xavier, for the introduction. I hope you can all see my slides. This is. I hope this to be like as interactive as possible. In particular, later I will try to dig into the actual code of MiniRust, and I've prepared some examples, but really those are more like starting points for discussion. So at any point, please interrupt me if there's questions or anything like that. If you don't ask any questions, I don't think we will fill this hour. So I'm relying on you here. All right, to get started, kind of a bit of context, what MiniRust is even about, and what I kind of hope to achieve with this. The goal of MiniRust is to specify what exactly unsafe code will do when it is executed. So you write some piece of unsafe code, it's a closed program, like it has a main function or something like that, it has concrete inputs, and you want to ask like what exactly could it output, or well, because there's no determinism, what is like the set of possible outputs. And this includes also whether the code has undefined behavior or not. I view this as part of what the possible behaviors of a program is. That's a very explicit thing this is supposed to capture. And then ideally we can do this in a way that is both precise and accessible. And that's kind of where things become hard. Explicit non-goals of MiniRust are specifying the behavior of the standard library. It's only about the language itself and like the parts that the compiler cares about for compiler optimizations, and the part that the standard library authors may care about because they also have to follow the rules about undefined behavior. And also a non-goal is to specify whether a given API expressed in like Rust types and callable from safe code is sound or not. That is a different question. It's related, of course, to say whether something is sound. Certainly you need a precise definition of undefined behavior, but it is a much harder question because basically what MiniRust specifies is on the level of validity invariance, which is directly about things that happen on the machine, where the machine is not kind of your hardware machine, it's slightly more abstract, but still it's a machine. Whereas the safe API business is about safety invariance, and to even state those, I'm pretty sure you need something like Iris and a lot of extra machinery like the lifetime logic and all of the stuff I did for Rust Belt. So that's a whole different discussion. And I don't even know how to make that discussion in a way that includes people that don't already know separation logic. So not a goal of MiniRust. Also something we have to do at some point, not a goal of MiniRust. All right, so how do we make a specification both precise and accessible? Well, certainly on the precision angle, like the first thing I do not want to do is, which I think is a mistake that we should avoid, is to use the axiomatic specification style. So by that I mean a style we basically have a long list of rules which just say, okay, like generally across all program execution, these are just a bunch of laws that hold that like the compiler guarantees that if you write programs in this way, then that will happen. And if you write them in that way, then this will happen. And everything you kind of want to claim about your program, you have to directly trace to one of those rules, and everything else is not something you can rely on. And the reason I think this is a mistake is that it's very easy with this style to leave accidental ambiguity in the semantics, and also to have accidental, like to add things to your semantics without even realizing that that's what you're doing. So this happened, at least in my view, quite a bit in C++ and in C, where these languages have a form of pointer provenance, and they have a form of uninitialized memory, which is different from memory that has any particular bit pattern. And I don't think many people that discussed the standard were even aware of at the time that this is what they were doing, but because they didn't say this, like the spec doesn't say there's pointer provenance. The spec says things like a pointer has to be derived from some other pointer to make something true, or like it's not allowed to do like when you do pointer arithmetic with the one past the end, sorry, when you do memory access with a one past the end pointer was computed by going one past the end of one array, that's undefined behavior. But if you do memory access with the same address in a different way, that's okay. These kind of things implicitly add pointer provenance, but it's very hard to even see that that happens. And so consequently, as these examples show, just adding a single clause somewhere in the middle of this, of like a huge 800-page document, impacts everything else in the semantics. Because once you have pointer provenance, now you suddenly need to specify what pointer provenance does everywhere else. Like how does pointer provenance act when integers are used, when you transmute a pointer to an integer, when you do arithmetic on pointers and all of that stuff, which the C and C++ specs say absolutely nothing about that, because they don't even acknowledge that pointer provenance is a thing. Now C is in the progress of fixing that, but like status like 3 or 4 years ago. And also because of this global impact, it's very hard given a program to figure out if your program satisfies all the axioms, and given an optimization, if this optimization is correct in the sense of, does it preserve the behavior of every correct program? So this is just basically not a solved problem. I think axiomatic styles might work very well for other parts of the spec, like certainly for things like the type system and the borrow checker, maybe for things like the library, I don't know. I think they are the wrong tool for something like the core semantics of unsafe code. So instead, I'm proposing we use an operational specification, which is kind of an alternative to the axiomatic style of specifying program semantics, where what you define is, first of all, the exact state that is relevant for program execution. This has to include everything that can affect program behavior, including affect undefined behavior. So this would explicitly include things like pointer provenance and uninitialized memory. And then you describe precisely how that state changes over time, as in during program execution. So that's an operational specification, and in a sense, this is something that is like this is certainly something that has been done before. WebAssembly is very explicitly an operational specification, and in a sense, JavaScript also is. Like if you read the JavaScript specification, they often, when to describe what a certain operation does, there's like a bullet point of like 25 steps. You do this, and you do this, and you do this, and you do this, which kind of very explicitly operationally describe one step after the other the things that happen. And the specification of the ARM instruction set architecture is also similar in that style. So this is and obviously it's widely studied in academia as well. So I think that's the right way to go. So that's kind of how I want to tackle this precise thing. And then the other question is, well, how do we make it accessible? And well, that's where I'm kind of mostly hoping, because I don't know how to scientifically evaluate how accessible something is. That's not my field. So I'm kind of observing that there is a very small gap between an operational semantics and an interpreter, like a piece of software that can just run some concrete program written in another language. So we can just use the interpreter to specify the semantics. Instead of specifying operational semantics in a mathematical way with inference rules and like, I don't know, reduction relations and something like that, we can just specify it as an interpreter. And then the hope is, because an interpreter is just a program, programmers will hopefully be able to at least understand what's going on there. That's kind of the idea. So what is MiniRust? Well, MiniRust is kind of, there's two parts to it. In a sense, first of all, MiniRust programs are described by an abstract syntax. So far, we don't have a concrete syntax, so like in terms of character sequences. It's more like the AST of sorts. You will see later. And then there's an interpreter that says how you can run a MiniRust program. So if you're familiar with Miri, this is a bit like an idealized Miri, without all the compromises that Miri has to make to be an actual practical tool that runs in finite time on real code. And like, I know Miri is slow, but like it could be a lot slower, and that's what MiniRust is in a sense. But of course, that's not the point. The point is that MiniRust is ideally, like Miri has to do a bunch of things which make it clever and much harder to read to get like to be not even slower than it is. And MiniRust will not do any of these things. In MiniRust, we will like the most important measure is to make everything simple and understandable and not fast. And of course, MiniRust then being written, like being an interpreter, the MiniRust interpreter itself has to be written in some programming language. And this targeting a Rust, like I could have written it in pretty much any language. OCaml might have been a natural choice if I would have been more of an OCaml person. But this being a language that targets a specification that targets the Rust audience, MiniRust is written in something I call pseudo-Rust, which is basically Rust, but you ignore some details around memory allocation and pointer indirections and stuff like that to make it feel more like a functional language with a GC. Okay, so that's like the preamble to set some context here. Any questions about that? Otherwise, we'll start jumping into some concrete MiniRust code, which is, I hope, what everybody is here for. Okay, looking good. All right, so let's start by looking at, I have too many tabs. That's a problem. Let's start by looking at the syntax, which I'm sure I have in some tab here. So this is what I mean when I said earlier, I guess I could make this a bit bigger. MiniRust has an abstract syntax. This is what that syntax is. So a MiniRust program consists of a table of functions that all have some kind of name. MiniRust function consists of a bunch of stuff declaring arguments and local variables and like not annoying bookkeeping things. And then the structure here is very much like what you might be familiar with from NIR if you've worked with that. So it's a control flow graph, a basic block-based language where a function is a bunch of basic blocks, each of which have a name. and there's a designated start block. And then the basic block is a list of statements that ends in a terminator. The most important statement is the assignment, which is where you finally get to the expressions, which is kind of what probably most people think of when they hear abstract syntax. So there's some destination place that gets assigned the value from some source value. There's some other stuff that's less important. Terminators are the usual stuff you would expect. You can jump to another block. There's a conditional. There's many things missing, obviously. And you can call functions. You can return from a function. And then in the expressions, you will see some of the usual things you would expect from a Rust-like expression language. It's not even very Rust specific. Like every constant is a value. You can load from a place to obtain a value. You can take the address of a place to get a value, and there's univariate binary operators. Many things missing. Again, that's not really the point. And then what do we have in terms of places? Well, the local variables of a function, including their arguments and also the return value, are places. You can dereference a pointer to get a place, and you can project fields and indices on places. Just to give you a rough idea of what the syntax look like. You will see some examples soon.
Ralph?
Yes?
I have a quick question about the syntax. I noticed that there's an annotation spec CR indirection over several of the.
Yes.
What is that?
For now, but to spoiler a bit, there's a master student, Rudy, who's in the audience. Hi, Rudy, who's working on making this into code you can actually run. And to make this actually run without a lot of pain, we need some help. I mean, to give the translator some help. And so the translator will insert pointer directions for you. But kind of as a in the rest of the specification, whenever you're dealing with value expressions, you can just imagine this is all by value, which wouldn't work in Rust because it's recursive.
Right.
So the translator tool specker will add these indirections, but you have to tell it where. But these are kind of not normative in a sense. They just help to make this consumable by a machine. Humans reading them can ignore these annotations. Yes, so that's the abstract syntax. And then the other thing, and that's probably pretty standard. I mean, every specification will have something like that. The other thing that's a bit less standard is that we also have this machine file here. So this is where we get into the point where this is an operational semantics. And as I said, the kind of first thing that you define in operational semantics is what is my program state. And that's what the machine is. The machine, MiniRust abstract machine, like all the fields of the struct type here, define what is the state of a running MiniRust program, which of course includes the source code that we're running. This is immutable. It better be. We'd be no self-modifying code on this level of abstraction, please. But then there will be some kind of memory, which you can see here is completely abstracted. This part of the semantics is kind of parametric in the memory model. There is some other state for the integer pointer cast thing, which we might talk about later, depending on your questions, I guess. And then there's a stack of so this is still the sequential semantics at this point. There's a stack of stack frames, where each stack frame has the function that it currently runs, the value of all local variables. No, sorry, not the value, the place where the value of the local variables is stored. Some stuff for return handling, and the program counter, the next thing to execute. And that's it. So instead of just showing you the step function, I think it would be probably more instructive to look at some examples, but it's kind of worth keeping in mind that this is the state that I'm kind of running on. And now the thing that remains is defining, to take a single step of program execution, how does this state change? Does it make sense? All right. To get started, I'm going to talk a bit about places and values, because this is something that I know confuses a lot of people in Rust. Well, I don't know if it confuses a lot of people. It certainly causes a lot of confusion when talking about Rust semantics with people. In particular, because there's a bit of there's some important pieces of syntax which are completely implicit when you write Rust yourself, which are explicit in MiniRust, and which were distinctions that are important for the semantics. So this is kind of a warm-up, if you say, if you want. So let's consider this simple example function in Rust, which just adds two numbers and return them. If we translate this to MiniRust, it would become code that looks roughly like this, where first of all, we can see that the return value is handled in mir. So there's a dedicated place. This is a magic identifier, ret, a dedicated place for where to store the return value. We can also see that there's type annotations in basically every operations. I will not always write them, but almost all operations have an explicit type, which you can just think of as Rust always inferring. And then the biggest difference, and which is the part that this is all about, is that we don't just say x here, we say load of x, which is necessary because x is a place, but addition works on values, and you have to turn a place into a value to be able to add them, which you do by loading from them. So in C terms, this would be an L value, and we would have to turn it into an R value, and there's L value to R value coercion indicating that this is happening implicitly. In Rust terms, it's a place and a value, but again, the load, or in mir, it would be a copy, is not written in Rust, but it's very important because this is the only operation, aside from assignment, that actually accesses memory. In particular, the star operator does not access memory. So that can be very confusing when you talk about dereferencing a pointer versus actually loading and storing from memory. Those are just completely different operations in Rust, and it's important to talk about the semantics on this level. It's important to see the implicit loads that are everywhere in Rust, which is kind of the point of this example. So let's see what would happen. Like, imagine we called this function with the arguments 13 and 29. I don't want to bore you with the details of how calling a function works. That's one of the most complicated step operations because you have to set up a stack frame. It's super annoying. Let's just imagine it's already set up and we have x and y, and they have some place backed in memory, and this is the value that's stored there. And now we want to execute this first and only statement in this function. So well, we do that by first evaluating the left-hand side of the assignment, which is a place expression, where not a lot happens because red is already a place. So the place expression red just evaluates to a place which points to the return place. This almost sounds rather tautologous. Not a lot happening here. The interesting stuff is on the right. So looking at the left-hand side of the addition, we first have to evaluate this place expression here in the middle. So we end up with a place expression of integer type that points to wherever the content of this local variable x is stored. Then we consider this here, which is a value expression that's less integer type. And then we evaluate this. That will now actually do the load for memory and give us a 13. And then we do the same thing on the right, where when we do the load, we get the 29. And now we evaluate this value expression, which takes the two values that we got from the left and the right, which are mathematical integers. There's no like modulo stuff going on anymore here. This is now a mathematical integer, and it adds them up, which is the result 42. And then because the plus here had type annotation I32, it does a modulo to put it into bounds of I32, which is already the case. So nothing happens there. And then finally, we come to the assignment statement, where we take the value that was computed on the right, which is 42, and store it in the place on the left. So one thing to observe here is that this is completely structural. Like if you think of the syntax tree behind this thing, evaluation works entirely by just starting at the leaves, evaluating the expressions to their values or the place expression to the places, and propagating that upwards. It's completely compositional and modular, and this is something that I think is very important, because one of the things I want to do with the semantics eventually is do proofs, and like proofs are no fun if you can't do these things modularly. And now I think I'm going to just show you some of the code inside MiniRust that like backs what I just said. So for example, here we have the code for evaluating a place expression, where if the place expression is a local variable, and we have to compute a place, then we simply do that by going to the current stack frame and looking up in the table of locals this variable, which happens to be that place. So I hope this is trivial. I'm not saying this because there's anything interesting going on here. I'm saying this to give you a feel for how everything looks. And the next thing that happens is this value expression load. So if we jump there, that's at least more than one line this time. There's a bit more happening. We're evaluating a load expression, which has, ignore this destructive thing. So the source is the place from which we are loading. So we, as always, first recurse and evaluate the place, so which turns the place expression into a place. Ignore this line, it's less important. Then we ask memory to please do a load from this place at the given type, which will be the type of the place expression. We skip the destructive thing, and then that is the value that we return. So this is how we turn it into a value, and I should probably show you what a value is. Do we have this open already somewhere? I do. This is the type of values in MiniRust. So as you can see, we have like some of the usual base values that you might expect: mathematical integers, mathematical booleans, pointers. I will explain later what a pointer is. And then we have some way to compose values where you can have a bunch of values in a list, which might be an array, it might be a struct, it might be a tuple, it might be any of those things. Or you can have a value which is like indicates some variant of an enum type. And then there's something special going on for units that we can get back to later. Right. And then finally, we have to do the addition, where which is a binary operator, which has two operands. So again, as always, the first things we do is we evaluate the left and right hand sides, which is where then recursively the things we just discussed will happen. And then we call eval bin op, which is not doing anything terribly interesting for addition. But I can show you, it's defined in a different file. But it will very unsurprisingly turn out that addition is implemented by adding two numbers. And then there's a bunch of stuff here to handle the modulo things. But these operators are mathematical operators. There's nothing, no machine bit width, anything like that going on. Okay, and then we come to finally we have evaluated the two leaves, the two sides of the assignment statement, right? So to evaluate the assignment statement, we first evaluate the destination place, then the source value, that's the stuff I just showed, and then we just store the place into the value. I hope so far so simple. All right, that's the warm-up. Now we come to the first kind of interesting example. We have a pointer and we load something from that pointer, right? So we consider a Rust program that just does a star PTR. If we make everything explicit, you can see that there's two loads here. First one goes to the place that stores your pointer value and loads the actual pointer. And then the second one does the load from memory. And there's the star in the middle. What does the star do? Well, let's look at it piece by piece. This is the value expression we are evaluating. So we start with this place expression, PTR, which again, that just points to our argument itself. And so load PTR is a value expression denoting the value that was stored in the pointer function argument. Star turns a value expression into a place expression. So now we have, again, of the same type. So no memory access happens here. This is, in MiniRust, actually, this is a complete NOP. That's one of the open questions. But at least for now, nothing is actually happening here. This is a value expression of pointer type. And this here then becomes a place expression of the pointee type. But a place expression is just in terms of what does it evaluate to? It evaluates to a pointer. So it's the same pointer, and we can look at it in the source code. The deref operation just evaluates the operand, asserts that it is a value. There's a little type system which ensures that this can never fail, and then asserts that this is a pointer, which can never fail, and then returns that pointer as the place that the star operator evaluates to. And then we do a load again, and now that's the actual pointer load from memory that you might have been expecting. And then we do the integer store. And now I think we can start talking about what actually happens when you store an integer in memory, because that's, of course, where things get interesting. Right? We have a mathematical integer. We know it is in bounds of the I32 types. There's some structure here that makes sure that that's the case. But so it's a mathematical integer, and we have to somehow put this into memory, which is not a container for mathematical integers. Memory in MiniRust is a container for bytes. Bytes are a bit more complicated than like you might expect, but they're still like basically bytes. So we have to figure out how we can turn a mathematical integer or like a MiniRust value in general into bytes. And this is where encoding and decoding comes in. That's what types in MiniRust are all about. So these notions of a typed store and a typed load that you've already seen, all they really do is, well, what does a typed store do? Let's look at that first, because we're talking about storing an integer. The first thing it does is it asks the type that we are using, which in this case will be I32, to please encode the given value as some list of bytes. So the value of bytes here is list of byte. And then it asks the memory model, which is abstract, to just store that list of bytes somewhere. So the how to handle the list of bytes, that's responsibility of the memory model. But how to convert between high-level value representation and low-level byte representation, that is responsibility of this language part of MiniRust. And so we want to see if you want to see how encode, well, what happens in our concrete case, you have to go to the integer encoding thing, which is somewhere up here. Oh, there. So how do we take a given integer value and encode it in a given type, where we first extract the mathematical integer from our general value type, and then we ask the friendly Indianness of our machine how on Earth large values are converted into byte sequences, which, as it turns out, is machine specific. But this does what you would expect it does, like a little endian or big endian. It correspondingly will just turn this into the appropriate byte sequence, and then does some type conversion with this abstract byte nonsense I will get back to later, to turn this into a list of bytes for the return value, which is then stored in memory. And the converse thing here, that's what happened when we earlier did the load from the raw pointer. So then, according to the type load function, which is somewhere down here, we first load the raw bytes from memory, and then we ask the decode function to please decode those at the given type. And that is something that can fail, because not every byte sequence is valid for every type. Hopefully that's obvious. And so if that fails, this is one of the cases where we have undefined behavior in MiniRust. And the decode operation for integers specifically starts by asserting that all of these bytes are initialized, because these abstract bytes which we're actually using track whether they are initialized or not, and then asks the endianness again to do the opposite of what happened down here, namely take a array of bytes of 256, like a U8 basically, and turn it into a mathematical integer. So now you can like already imagine what would happen here if we would put some uninitialized, if we would have some uninitialized memory here. We can now explain why this little program here is undefined behavior if the pointer points to uninitialized memory. It is undefined behavior because when we compute this here as a value expression, we want to produce a mathematical integer. That's always what happens when you evaluate a value expression of integer type in MiniRust. And there is no mathematical integer that corresponds to uninitialized memory, so we raise undefined behavior. It's not a valid encoding at this type. I should probably show the abstract byte type, because things might make more sense if I do. Ignore provenance for now, but basically an abstract byte, it's an option of a U8 if you don't have provenance. Yes, maybe Alnit. Well, so maybe Alnit is a union. So then if we can now imagine doing the same exercise at a bunch of different types, and that can teach us interesting things. Right? Before jumping to maybe Alnit, let me first jump to Bool, which is interesting, of course, because not all bit patterns are valid for Bool. So we will not be very surprised, hopefully, to hear that Bool does a little case distinction about the byte that it got, returns the corresponding mathematical Boolean, and says undefined behavior if this is not 0 or 1. And then the opposite thing happens for encoding. So in a sense, all of this business that we know about in Rust as validity invariant is completely, in MiniRust, completely arises just from the fact that this decode operation can fail. So there's no explicit validity invariant in MiniRust. It's just a fallible decode. And yes, now we could imagine that this wouldn't be I32, it might be maybe Alnit of I32. Maybe Alnit is a union type. So then we would use a different value representation. That's the thing I skipped about earlier. Ignore the nested lists for now. Just imagine this would be a single list. The real world is a terrible place, and that's where they are nested. But like, let's imagine we are in unicorn land. A union in this proposal for MiniRust, its abstract mathematical MiniRust value is literally just a list of bytes. There's actually no abstraction going on. It's a direct match to what happens in memory, is what happens in the union. We don't try interpreting anything. So correspondingly, the encode and decode operation for unions just don't do anything. They just take a list of bytes and like put it in there, and then for encode they put it back in memory. Which means if you do a load at maybe Alnit type, this will never be undefined behavior. Well, assuming that the memory itself, like the pointer exists, like it's dereferenceable and all of that business. But in terms of the contents of the bytes, it will never be undefined behavior. The decode function for union will never return none. Because we can just take any sequence of abstract bytes and shove them into this union type. So this also explains what happens with maybe Alnit. Guess I think I went over all of this. Now, before I go on, I have to briefly talk about another more or less contentious topic, which is pointer provenance. So my claim, which at this point I think is increasingly something that is getting at least accepted in Rust, is that pointers are more than just addresses. So what do I mean concretely by this? Well, if you consider a function like this, which takes 2 pointers and requires that they are equal, otherwise we have a panic, then I claim it makes a difference whether we dereference the right pointer or the left pointer, right? If you have a direct model of Rust in terms of what happens on the underlying hardware, where pointers indeed on most hardware are just addresses, then of course it makes no difference at all. Once we compare that they're equal, we can deref right, we can deref left, it's the same address, like what difference could it make? But in Rust, it can make a difference, which we can see, for example, if we consider a little example like this, where we have 2 local variables, which will happen to be allocated directly next to each other in the stack, at least in the debug build on the current stable compiler. So that if we take the address, or well, if you take a pointer to X and add 1 to it, this will happen to be the exact same address as a pointer to Y. But of course, in Rust, we still say it's not okay to just do pointer arithmetic from 1, and not just in Rust, by the way, also in C. You can't just do pointer arithmetic from 1 local variable, happen to arrive at the address of another local variable, and then just assume that that makes any sense and like do the right there. So like it's completely okay, obviously, to read from &y, but it's completely not okay to read from this monster of a thing, even though they are the same address. So this program here would be okay because we're reading the right pointer, but if we read the left pointer instead, then it would not be okay. So this clearly shows that there is more to pointers than just their address. And I have a second example here, which just shows that with aliasing, there's even more of that, but I don't. I would skip over that unless there are some more detailed questions about this. That was not a question, that's a statement. All right. Okay. So in the second example, let's now look a bit at what happens with provenance in Rust. So to that, we look at this completely ridiculous piece of code where we take a pointer to a pointer thingy and a value that we just need to take the address of something because I didn't want to like add local variables. So this program clearly makes no sense. This is just to demonstrate what happens, where when we do this, when we make this explicit in MiniRust, there's actually not a lot. I mean, there's a bunch of type annotations, but the only thing otherwise that gets added is this load that we always have, and we use a local variable by value. The question, of course, is what happens when we actually evaluate this program. So let's again go over the expression starting at the leaves. As always, this is how evaluation works. So the first thing that gets evaluated is &val, where, well, the first thing that gets evaluated is val, which is a place expression where nothing happens because that's just the place of the local variable. And then &val, ampersand is also utterly trivial. It's the exact opposite of star. So that makes sense, hopefully. Both are utterly trivial, where we evaluate a place, which gives us a place value, which is a pointer. And then we just return that as a value, as a pointer value. So nothing happens. What is a pointer value, you might ask? Well, a pointer value consists of 2 things. It consists of an address and it consists of provenance. For now, we don't say what exactly the type provenance is. We leave this abstract. It will not matter for most of MiniRust. The thing that is important here, or will become important at some point, is that this is an option. So like there's the notion of a pointer that has no provenance. That turns out to be super useful to specify these semantics. This corresponds to the pointer : invalid function, if you are curious. Yes. So now, after evaluating this thing here, which is a value expression, we now have a value that stores a pointer, so some address and some suitable provenance. And now we are asking it, remember, the next thing this does is *ptr equals. So we're now asking it to store that value in memory, which, remember, means we are going through an encode operation for pointers. So how do we encode a pointer? Well, we have a helper function for that. I'm not entirely sure anymore where we have a helper function. It used to be necessary, but anyway, where Well, the first thing that we do is we like, let's ignore provenance for now. We just care about the data, and there we do exactly the same thing that we would do for an integer of the same size. But we ask the endianess to please encode that pointer for us. But then when we construct the list of bytes for the return value, we don't just make these bytes initialized, we also put the provenance of our pointer in every single one of these bytes. So that is how provenance is kind of remembered when we encode things into the memory. And then conversely, when we decode a pointer from memory, we will look at these provenance annotations and use them to compute the provenance of our pointer. Now, and for now, just assume, I mean, there's a bit of interesting stuff going on here, but for now, just assume that all of these bytes have the same provenance. Whenever that is the case, then the resulting pointer that you decode from memory will have exactly that provenance. So there's the important property satisfied here that if we take a value and we encode it, and then we decode it again, we get the same value back. Or at least a closely related value. There's a bit more complication going on. It's not always exactly the same. So what this means now is that our bytes in memory can carry provenance, which is absolutely necessary because we have values that carry provenance. We have these pointer values, and we need to be able to store our values in memory and get them back without information loss, because that's something we do in Rust all the time. So clearly, we have to have some way to store provenance in memory. And that's why our notion of bytes is a bit funny and has this option of having provenance in any initialized bytes. Okay, so now we could imagine doing some other more weird things to this example. We could, for example, imagine doing a load at integer type. Like, so this is just extending the program, but this is the same thing that we had before. And now we go to the same pointer and we dereference it again, this time at type usize. MiniRust is sufficiently loosely typed that this will just work. And we just load an integer of appropriate size from that pointer. What happens now? Well, you can just look at the code and see what happens. And we will see that here, what we're doing is we're calling the data function on abstract bytes, which is defined wherever I have my abstract byte thing here, which just throws away the provenance. So what this specifies is that when we are loading, an integer from memory, we don't care whether they have provenance or not. But also, if there was provenance, we completely forget about it. So if we now extend this program and store the integer back in memory at the same place, well, there's no provenance. So we'll now overwrite those same bytes with bytes that have the same integer values in the U8 part, but don't have any provenance anymore. So if we now try to use them again as a pointer, we would get undefined behavior, because now we are decoding a bunch of bytes with no provenance, which gives us a pointer with no provenance. So this thing here will be none. And I mean, basically, certainly, I have kept the memory model abstract, but it's basically certain that the memory model, if you give it a pointer without provenance and you want to ask for actual data, like not just a zero-sized axis, but some actual bytes being loaded, it will just say, nope, there's undefined behavior. You can't deref a no provenance pointer. So this explains how, at least it's a MiniRust explanation of what happens when you transmute a pointer to an integer and back. That's basically what happens here, right? By doing these typecasts. Right, so that's how we get UB. I have a third example, but I think for now, I will skip over that. It's about padding. I'm happy to go into it later, but for now, I would like to close and open to your questions. So to summarize, in MiniRust, expressions, where most of the action happens, are an interesting interplay of a back and forth between place expressions and value expressions, where place expressions evaluate to places and value expressions evaluate to values. Very surprising. Where places are pointers and values are this big enum you saw, like where there can be mathematical integers, pointers, compound types, anything like that. And types, the key role that types play is they define how to encode values at lists of bytes and how to decode those lists of bytes back into values. And in this encode and decode function, there's a lot of interesting information going on there. A lot of the interesting questions about unsafe code behavior when you do like low raw memory manipulation are answered by those encode and decode functions. Like all of the stuff around how pointer provenance is preserved when you load things at different types, or how validity invariants come to be, and also all of the ways in which padding is magic. That's the part I skipped over. It's all in these encode decode functions. Somebody was saying something? No? Okay. I kept the memory model abstract, but the language does define how provenance propagates through all of these operations. MiniRust comes with what I call a basic memory model that kind of shows how to implement the memory model interface, and that has a non-trivial notion of provenance, but that is not an actual proposal for the memory model for Rust, because it does not do anything with aliasing. So again, that's another thing I can go into a bit more detail if you want to use the last 15 minutes for that. Can show you how the basic memory model works. But of course, there is still a lot of things that need to be done. First of all, it would be really nice if we could actually execute MiniRust. I mean, it's an interpreter, but so far it's just written in essentially pseudocode. But Rudy, as I already mentioned, is working on making that happen. So that's super nice. We might soon have the first test cases, and we'll see how everything I explained is wrong and actually there's bugs everywhere. I don't know, probably. We obviously need to implement a ton of missing features. I mean, you've seen our list of unary and binary operators. There's like not a lot there. Most of this is not terribly interesting, and it's not really what the unsafe code detailed questions are about, so I didn't really focus on that. We need a memory model that actually has aliasing constraints. I mean, stack borrows could fit that interface. Also, I'm working with an intern currently on kind of a next generation aliasing model that fixes a bunch of the problem with stack borrows. So there's like still a whole bunch of open questions there. But the nice thing about the structure here is that we can keep completely separate, or at least mostly separate, the discussion about memory model details from the discussion about type encoding, decoding, places, values, integer pointer cast, and all of those things, which are treated completely independently from the memory model in MiniRust. We need to make sure that this model actually matches what real Rust does. So there's like some testing and fuzzing and things like that I want to do. Obviously, a lot of it. There are a lot of open questions. If you've seen as I scrolled through these, there's like these to-dos and fix-me's everywhere. I tried to make sure that whenever I was aware of dissenting opinions on certain things, which I decided to leave a note. I'm not sure if I captured them all, but even with that, there's a lot. So like this MiniRust is not the specification how it will be. It's my proposal for how to currently answer many of these questions like in one package, already with a bunch of very interesting input from some unsafe code guidelines people who helped me figure out some of these details, and in particular, the model of provenance changed quite a bit through those discussions. But still, it's like very few people that had input on this. So not the final thing. There's a big gap, obviously, between surface Rust and the MiniRust syntax. There's many things we have in surface Rust which don't exist in MiniRust, like dropping, automatic implicit drops. And there's things in MiniRust which don't exist in surface Rust, like the exact markers for what the lifetime of local variables are. All of these things are defined by the translation from surface Rust to MiniRust, which I view as yet another separate component of the entire story around the operational semantics for Rust, which is yet another project, essentially. And so if this kind of stuff interests you, then I guess keep your RSS readers or something hot, because hopefully soon there will be an operational semantics team that in Rust as an official team. There's currently an active RFC for that, which will have the goal of answering all of these questions. Maybe with MiniRust, it's going to be my proposal to the team to base the semantics around that. We'll have to see what the team says about that, and I'm sure it will change in one way or another. But yeah, that's where these things will hopefully be happening. So with that, thank you very much. And we can use these 10 minutes for any questions you might have, or I can go into a lot more detail about any of the things that I didn't have time for.
Thank you very much, Ralph. And I see we already have a question from Pointer Vendor, who is asking, when loading a pointer to B through a pointer to A, e.g. with type A equals to star mute B, and then dereferencing star mute A, does MiniRust place any constraints on the provenance of the pointer to B based on the provenance of the pointer to A?
No. It's just another load. Like, I mean, you deref A, you get a place in memory. At that point, it will check whether the provenance that A has is actually allowed to do the read you want to do. That's like aliasing model, memory model things. But then once that's done, the memory model will just give you the bytes, the list of abstract bytes stored behind A, and MiniRust decodes them into B. And what matters is the provenance stored there. So no, this is something that for like I've never seen any memory model or any compiler optimization where loading a pointer through a pointer kind of infects the inner provenance. I have several times seen people being confused about that. I have no idea where that comes from, but no, I don't see any reason to do that. Let me put it that way. Maybe there's something I'm missing. Maybe there's some good reason to do this. I'm not sure if you want this to happen or if this is something you were afraid might happen. But no, I don't have any plans to do that. And Miri certainly, okay, good. Miri certainly doesn't do anything like that. So yeah, I hope this is not a natural thing people expect to happen, but more like an abundance of caution question here. But yeah, currently the MiniRust structure wouldn't, like, I'm not even sure how you would do that, because when you load, I mean, there is the memory model operation, the memory interface. Yes, here. This is the load operation. It gets a pointer with some provenance. It will check if that pointer has the right provenance, and then it is supposed to just give you the bytes as they are stored there after having checked that you're allowed to access those bytes. But which bytes you get do not depend on which provenance you put here. Only whether you are getting the bytes depends on the provenance. That's the idea anyway.
I also have I see there's a question from Sasha, who asks, how long until you think we have a working Rust and MiniRust plus interpreter actually working? Because he has experiments he'd like to perform on this.
I don't know, Rudy. I think the master thesis still has 5 months planned until it's going to be finished and written up. So that should be an upper bound for having something.
So I have a couple additional questions. My first one was sort of a meta question. Do you feel like you've learned anything new about Rust by working on MiniRust? Like, have you uncovered any previously unknown gaps in the Rust specification and the Rust understanding of its semantics?
I mean, let me first answer the question you didn't ask, which is I think I learned a lot about Rust before writing MiniRust. Like, MiniRust is something that has grown in my head over years, and there was at least 18-month period where several times people asked me, like there were discussions about Rust specification and things like that. And I was like, yeah, I have an idea for how to do all that. It's all in my head. I just need to get out there. But that's like a very bandwidth limited channel. So that took a lot longer than I had hoped. I was hoping to do this 2021 already, but oops. And so this is, at least at the beginning, MiniRust was more the result of learning a lot of things about Rust and like how to consistently think about pointers and values and this encode decode thing and all of that stuff, and like an attempt to communicate it in a structured, systematic way, which I'm not sure will work, but it's the best way I've found so far to try and communicate this to other Rust people. The ensuing discussions, well, certainly as I mentioned, the provenance behavior changed a bit. What exactly the integer decode function does on bytes with provenance is not anymore what it used to be. So there I did learn some things, I think. There's a bunch of stuff I skipped over, but there is a bunch of axioms that the encode and decode operations satisfy, which corresponds to something like Galois connections. That not too surprising, but there's round trip properties you want to have. If you do an encode followed by a decode and I do a decode followed by an encode, you want some kind of relation. One of them is equality, the other one is not equality, which will not surprise anyone who's done static analysis. Or if you're into category theory, you can think of it as an adjoint. Not that that's helpful, but you can do it. But there also, again, I learned like the exact order relation that is used to define this Galois connection is something that we worked out in that time. And then after defining that, I realized that there is actually one thing that Miri does, which is in a violation of this order relation that I want to have, which currently Miri still does because it's just more UB, and I don't want to allow this kind of code yet. But it led me to think that we should probably change this, which is hard because it means first changing LVM, which is always a terrible thing to have to do. But at least I'm pretty convinced now that we have to do it because that's the only way that this semantics as given right now here is coherent. If we can't do this one tiny change to LVM, this will ripple back and affect a whole lot of things all over MiniRust. So it's one of these tiny things that I learned, I think.
Yeah, fascinating. So we have a couple other questions that have popped up in the meantime. VA asks, at which points UB can happen? I notice expressions can be arbitrarily large. Can UB happen when evaluating an expression?
There can be certainly UB within expressions, like because load is an expression, and there can be UB in every load, because the pointer might dangle, or you might not have the right provenance to the load, or the data behind that pointer might not be of the right type. Other than that, I'm not entirely sure. I haven't grabbed for throw UB everywhere. Okay, so we also have undefined behavior on place expressions. When you project to an array index that doesn't exist. I hope that makes sense. Whenever you reach the unreachable terminator, obvious undefined behavior, some annoying things in function calls. Regarding the other question, so MiniRust does not have any UB on integer overflow. Integers are just this always wrapping arithmetic period. If you write code like this nested plus minus in Rust, at least in debug mode, it will translate to MiniRust that does explicit overflow checks and panics, which is not undefined behavior, it's just a panic. But on the MiniRust level, just like in Mir, this particular example here is guaranteed to return 5. Because it's just going to be, what it concretely will do is it will add the mathematical integers 5 and max u32, then do modulo 2 to the 32 on the result, then subtract max u32 as a mathematical integer, and then do modulo 232 as a result again, and the result will be 5. But that's, I think I had somewhere the bin op stuff. Now I have too many tabs, so I can't even see the file names anymore. Great.
There's another question from Florian, who is asking, if I wanted to start a formal methods project about unsafe Rust today, would you say that it's possible to use MiniRust as a reference for the semantics?
I mean, this is my proposal for semantics. So you certainly can't claim that this is normative in any sense. I'm just one person in the unsafe code guidelines group. I might be one of the initial leaders, but still, this is not normative in any way, and I expect it will change. So yeah, but of course, if you're okay with that, then I guess it would be something you could do. I mean, I have plans along those lines. I want to, like, as I mentioned, we already have we're actively working on getting a translator from MiniRust from pseudo-Rust into Rust so that we can run the MiniRust interpreter. Of course, what I also will want is a translator from pseudo-Rust into Coq, so that we can start proving theorems about it. And that is something I have a lot of plans for, which will probably span multiple PhD theses. But the idea is that something like MiniRust could be a source of truth for all sorts of things that talk about the semantics, and not by manually translating them, but by doing this automatically as like derived artifacts, which I think would be super nice. But that will still take a bit. So if you want to start it now, you would have to probably do the translation by hand. I don't know.
Yeah, and perhaps follow the operational semantics team and its development if you care about a normative semantics.
Yeah. I mean, right now I also expect it would be a lot of work to actually do verification on this. MiniRust is big. Like, there's a lot of layers. I mean, MiniRust is small, but once you add all the missing features, it's big. And it's much bigger than the languages we usually consider when we do formal verification in a theorem prover. So it heavily depends, I would say, on what the formal methods project is, because that could be anything from like doing proofs by hand in Coq to, I don't know, maybe some kind of symbolic execution thing on top of this could actually work. I don't know if like Sasha would know more about whether it's possible to like put this to have Kandi implement exactly this. I don't know. That might be interesting.
So I think we're up against our time limit here, but I was wondering if you could comment quickly on the issues around aliasing that you mentioned earlier.
Viper, not Viper. They're very different tools. Oh, somebody already answered. Great. Thanks, Vir. Issues about aliasing. I mean, we're just currently not answering the question. Like, MiniRust doesn't do anything with aliasing. It defines the language itself, doesn't even talk about memory. It just says, well, memory is a thing where you store bytes, and it has its own quirky notion of what a byte is. But Memory, like you can give it a list of bytes and then you can get it back later, and that's it. There is a simple memory model which can be used as an interesting illustration for how to think in a precise way about provenance, because it already has provenance, but it doesn't do anything with aliasing. But of course, I mean, what you would do with aliasing is there's these parallel lines of work to propose aliasing models for us, where we have stacked borrows as the current proposal, and we will hopefully have another proposal also soon, and we could implement the memory interface for both of them and plug them in. And the kind of part of the point here is to factor these discussions a bit so that they don't have to be all entangled. Yeah. And also, by the way, one thing, since I mentioned earlier that this is meant to be like part of the goal here is accessible. This is a soft goal in the sense of I don't know how to evaluate it. So I'm very happy about any kind of feedback for how well this kind of presentation of a specification works for you, like whether you can read a part of MiniRust and be like, okay, now I understand how something works, and suggestions for how to make it better. I mean, obviously there's a whole bunch of in the formatting we want to do better. I mean, I've seen the Pharisee specification and how everything is like linked and anchored and all of things, and it's amazing. And I want to also be able to just like have links that go directly to a single line somewhere in here or something like that. There's a lot of stuff we can do there, I hope. But in terms of the general structure of having this kind of literal code thing with like markdown files and a bunch of text that, I mean, we need more text. We need text that actually explains not just what is, but also why it is. That's something we have to add at some point, all of those things. But in general, if this kind of format is something you think can work or not, that would be super valuable, because I don't know of any language that is specified in this way. So it's kind of a risk. On the other hand, I think for me, it's the way that would work best to specify something like Rust. Well, okay, a Coq specification might work best, but I don't know. I know that won't fly for everyone. So yeah, we better, if there's feedback there, I think we better get it early rather than we already have written the entire Rust spec and then we learn that nobody can read it. So that would be super valuable. You can, I mean, if you just go to Zulip, if you don't have your comments right now, just go to Zulip to the unsafe code guidelines stream and leave a comment there.
And if people wanted to read the specification to give you feedback, where could they actually find it?
Oh yeah, I should have put a link to the thing into the presentation, right? That would have been smart. It's here, the URL. I don't know if that's big enough that they can read it. Can do something ridiculous where I put it into some editor field. Right, it's on my, oh, this works great. It's on my GitHub, Ralph /MiniRust.